We're going to do a fast and furious review of the second semester final exam. And we'll do this in the next 20-25 minutes. And then next time you'll see I'm going to give you an equation list and to use and go over that. So this review will actually be in two parts. So Unit 7, and I am looking at the final exam. This is right here. Now, this is last year's final. I'm going to modify it a little bit, but it will basically be about the same. I'm just going to copy and paste from it. Unit 7, momentum. What do you need to know? Well, first of all, what's the definition? What's the definition of momentum? Make sure you look that up. What's the equation for it? Well, momentum is just the mass times the velocity of an object. Okay, and so that's basically the definition of it, isn't it? But you need to know the definition in words. As well as picture, notice the momentum vector is in the same direction as the velocity vector times the mass of the object. So it's just a matter of how much stuff is moving, how fast. Then we talked about the impulse momentum theorem. The impulse momentum theorem. Very simple. You have to know what an impulse is, and you have to know what the change in momentum. An impulse is a force times time. If you apply a net force to an object for a period of time, that will cause a change in momentum of an object. So I could, and remember that for the purposes of this class, that we're not going to change the mass of an object. We'll apply a force to an object whose mass is constant, but so therefore a change in momentum is just the mass times a change in velocity. Now, one of the things that you'll notice here is that this is a product, that a quantity, change in momentum, is equal to the product of two other quantities. And one of the things that we said is that if we graph this quantity, force, as a function of this quantity, time, and let's say I give you a problem like this, and I'm not going to put any numbers on here, but if I give you a problem like this, that this quantity is the product of these two, so that the area underneath this graph is the change in momentum of the object. Okay, so you would just divide it up into rectangles and triangles and add up the area. And that would be the change in momentum of the object, and then you can use that to figure out what the final velocity is or whatever. Okay? Okay, and so now we are, that leads us now into conservation of momentum. When is momentum conserved? Well, if the net force on an object is equal to 0, then the momentum is conserved. So now, remember that force. Well, no, that's good enough for what we're doing here. If an object is in equilibrium, its momentum is not going to change. Or if a system of objects are in equilibrium, or if there's no net force on a system of objects, the momentum is not going to change. Really, this is what Newton said. We said that, let's take a look at the impulse momentum theorem. Force times time equals delta P. If we divide both sides by delta P, we get the net, this is the net force, is equal to the rate of change of momentum. Delta P over delta T. Well, remember that this is mass, delta P is mass times change in velocity. The change in velocity over change in time is acceleration. So this is where you get F equals mass times acceleration. But if the net force is 0, then that means the rate of change of momentum is 0. That means there's no change in momentum as time goes by. Now, under what circumstances can that occur? Well, let's say two objects collide. Remember when we said that two objects collide, bam, they hit each other with equal and opposite forces for exactly the same amount of time. If you look at this as a system, as these objects collide, there is no net force on your system. This force would serve to cancel this force as far as your system is concerned, and you're not changing the momentum of the whole system. So here we have P initial, therefore it would have to equal P final. Initial momentum equals final momentum. And so if you have two objects, you go M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. We worked problems like that on the back then. So there could be a collision problem, a simple one on the final. So this is so the net force is equal to 0 when you have collisions. And remember explosions. When we exploded stuff, parts flew in all directions, but the momentum of the entire system remains the same because there's no net outside force acting on your system. So this kind of takes care of Unit 7. It's the main Unit 7 ideas. Let's go to Unit 8. Unit 8 was work and energy. Make sure you understand what energy is. That is, to be able to define it. Energy is the capacity to make a change in your environment. And there's various kinds of energy. One of the most important kinds we said was kinetic energy. Okay, if something is moving and has mass, it has energy. We developed an equation for it. I'll just give it here. You probably remember it. K equals 1/2 the mass times the velocity squared. Then we had gravitational potential energy. We called that U sub g, and that was equal to the mass times the gravitational field. This is the force of gravity times your height. Another way of saying gravitational potential energy is the work that gravity can do to pull something down to the ground, or whatever your reference point is, whatever your height is. Now we had other kinds of energy, elastic potential energy, called that U sub E, and this is the energy stored in a compressed or stretched spring or elastic band or any kind of springy material. We're not going to use the equation for that. We did kind of develop one, but it's not going to be on the final. But here is what's going to be on the final. We're going to talk about mechanical energy. And mechanical energy is the sum of these three kinds of energy. E equals the kinetic energy plus the gravitational potential energy plus the elastic potential energy that an object or system of objects might have. Now these are the ways we store energy in the environment. We store it in motion, we store it in a gravity field, we store it in a stretched or compressed material. And we call this mechanical energy. But we can also transfer energy by doing what we call work. Work is a way of transferring energy by means of a force. You know, for example, if I throw a ball, I'm applying a force to the ball with my arm. I'm transferring the energy that was in my arm and the muscles of my arm. I'm pushing through a distance, giving that ball kinetic energy. So that's where the kinetic energy of the ball came from the chemical potential energy in my arm. I didn't list that up here because it wasn't a mechanical energy, but there's chemical, there's nuclear energy, there's different ways that energy exists in the universe. Work is a way of transferring that energy from one system into another system by applying a force to it. The equation was that work is equal to force times a displacement times the cosine of the angle between the force and displacement vectors. So make sure you know what these variables are and how to apply them. And this is how we get the units for energy, by defining what work is. Some people say energy is defined to be the ability to do work. I don't really like that definition, but I like to use work, though, as a way of defining what units for energy are. The units for energy are newtons times meters. And a newton times a meter is a joule, which we abbreviate with a capital J. Now, we talked about mechanical energy. If and only if, if and only if the only forces doing work are gravity and springs, or some elastic material, then the initial mechanical energy of your system will equal the final mechanical energy of the system. Because if gravity's doing work, then all you're doing is turning gravitational potential energy into kinetic energy. If gravity's doing positive work, if gravity's doing negative work, then we're turning kinetic energy into gravitational potential energy. So go back and review those videos if you want, or think about when I was pouring the water in those beakers. And this allows you to solve a lot of different problems. We have the work energy theorem. And I really should have mentioned this earlier, probably up here, because really it's the work energy theorem that we use to define what kinetic energy is. But the work energy theorem says if the net force is doing work, the work done by the net force, that's W net, the work done by the net force must result in a change in kinetic energy of your object. So you look at an object, look at the net force on the object. If that net force is doing work, the result of that work is to change the kinetic energy of your object. And they call that the work energy theorem. So this is the net force times the displacement times the cosine of the angle between the net force and displacement equals K final minus K initial. Remember, anytime you have a delta, this is the same as K final minus K initial. So there could be a problem on using that equation, the work energy theorem. And that should take care of Unit 8. Unit 9 is thermodynamics. And the basic ideas in thermodynamics is, well, the things have a temperature. The temperature, be able to go, make sure you can go from back and forth from kelvins to degrees Celsius. Look up that equation. Mainly, though, we talked about heat transfer. That is, if I have thermal energy that's flowing, well, I'm always going to get thermal energy to flow if I have a temperature difference. And heat always flows from high to low temperature. So we had Q equaled mc delta T. This was for if I'm increasing the temperature or decreasing the temperature of a material, but there's no phase change. This is mass. This is specific heat capacity. This is your temperature change, either in kelvins or degrees Celsius. Or if you have a phase change, we had heat is equal to mass times the heat of fusion. Heat of fusion is the energy absorbed when you melt a material, a certain mass of material, or the heat that you have to extract, or the heat given off by a material if you're going to freeze it. Remember, freezing and melting are just the opposite processes. If you're, you want to freeze ice cubes in your freezer, you have to extract thermal energy from the water so that it will freeze. Or if you take those ice cubes once they're frozen out, you put them in your drink and they absorb heat until it's all melted. And so this allows you to figure out how much energy it will take to do that. And of course, we had one more phase change, the heat of vaporization. This tells you how much energy it takes to vaporize an object. So, or some stuff, if I have a glass full of water and I boil it away, this tells you mass times this, the mass of the water that got boiled away, times that tells you how much heat you had to put into that water to get it to boil away into a vapor. Conversely, if you have a bunch of water vapor up in the sky or in your room or something, and you want to condense that back into a liquid, well, that's going to release thermal energy into the environment. That's what clouds are doing. When you see a cloud forming, water is condensing back into a liquid form, little tiny liquid water droplets hanging in the sky, and that releases heat. So heat can be absorbed. Usually it's negative if it's absorbed, or it can be released. Okay, so no, if you're absorbing heat, that's heat into your stuff. That's positive heat. If you cool it off, or if you freeze it, or if you condense it, then it's giving off heat, and that would be negative. Okay. We had this idea of entropy. Entropy is really the second law. Just make sure you look it up. The basic definition: things become more disorderly. Okay, as heat flows from high to low. So this is low temperature stuff, maybe ice water. This is high temperature stuff. Heat will flow from high to low temperature. So there's your heat flowing. And by doing so, we reduce the order in the universe. Think about it. What are the odds of finding a bunch of molecules moving slow over here and these moving fast over here? It's pretty low odds. So as time goes by, the heat will flow over here, and you'll get a more random, less organized arrangement of molecules, and thus we say the entropy increased. And then we talked about heat engines. This is like an internal combustion engine in your car. You explode some gasoline. That makes a very high temperature gas. It pushes on some mechanical devices. We call that the heat engine. Heat flows from high to low temperature, and as it flows, some of it is turned into work. So this is the heat that flows out of your high temperature. Much or even most of the heat, it flows into the low temperature reservoir. That's your car, that's the environment. And so if you add these together, the heat that leaves from a high temperature has to equal the work done plus the heat that flows into my low temperature reservoir. This is conservation of energy. And the fact that heat will always flow from high to low temperature is the second law of thermodynamics, which also describes what entropy is. Entropy means that heat will always, No matter what you do, no matter how hard you try, heat will always flow from high to low temperature. Okay. That should take care of Unit 9. Oops, I forgot to label it. This is Unit 9. Okay. Now let's do Unit 10. I want to use plain water. Here's the essential elements of Unit 10. We have protons. Protons have a positive charge. We have electrons. Electrons carry the negative charge. So this is protons, and these are electrons. And they are attracted to each other. So they will pull each other together. Or if you have like charges repel. And the force of repulsion or attraction is defined by Coulomb's law, which says that the amount of force of repulsion or attraction between isolated charges is, well, it depends on what this charge is, and that's what we use, the letter Q, to represent charge. And this charge, maybe this is Q1, this is Q2, and it depends on the distance between them squared. Sometimes I use R, sometimes I use D, doesn't matter. The distance between the charges. Now you have to know what K is. This is all you can change, and K is the constant that tells us how strong the electric force is, and it turns out to be really strong. K equals 9 times 10 to the 9 Newton meter squared per Coulomb squared. That's 9 billion newtons if you separate 2 coulombs of a coulomb of charge and a coulomb of charge at 1 meter apart. You'll have 9 billion newtons. Don't do that at home, people. You'll shred, you know, your house will explode, okay? So the electric force is very, very strong. Remember that the elementary charge is 1.6 times 10 to the negative 19 coulombs. This is the charge. I'll put plus or minus, right? When would it be plus? It'd be plus if you're talking about a proton. It's negative if you're talking about an electron. And so that, you know, a coulomb of charge is what we use to measure the amount of charge with, which we'll talk about on Monday for the second half of all this. Now, sometimes I can create an electric field. Okay, an electric field, by definition, is the force that my object feels. If I put a charged object right here, and it feels an electric force, it could be a Coulomb force like this, or it can just be some divided by the charge. Here you get newtons per Coulomb are the units. That's what the electric field is. If I put a charged object in space, and it feels a force because of its charge, therefore it is in an electric field. Now what causes an electric field? Separated charges. Remember, electric field lines, they start where at positive charge, they end at negative charge. Okay. And let's see. Now this force can be the Coulomb force, and one of these charges will be your test charge, so it'll cancel out. So if you've got a point charge, the electric field is KQ over R squared. Use R instead of D in that case. And that tells you what force there is. Now if you know what then we have this thing called voltage. A change in voltage is equal to the electric field times the displacement. Yeah, I'll put a vector hat on this so you won't think it's mechanical energy. Dotted with delta x. It is a dot product. It's E times delta x times the cosine of the angle. I don't think we worried about that. But look, this is newtons per Coulomb times meters. What's a Newton times a meter? That's a joule. Joule per coulomb. What is a joule per coulomb? That's a volt. So if I move look, there's potential energy here, right? If I've got an electric field and I've got a charge right here, boom, it's going to accelerate to the right because it's got a force on it. That acceleration will cause will give it kinetic energy, and therefore we're doing work, therefore we're transferring energy. We've got some kind of energy going on here. Well, that energy is stored in here. We call that the electric potential energy, and then we divide it by the charge on there, and that's when we get voltage. So, and I am kind of rushing through this. Now, I think what I'm going to do right now is stop here, and then I will finish. I'll do Unit 11, and then I'm going to give you a quantity chart and equation list that you can use for the final exam. I'll do that next time. That is all.